Assalamu alaikum warahmatullahi wabarakatuh. This is Dr. Ali El-Moursy, and this is the microprocessor and assembly language class. This is our first recorded session for lecture number 17. As you can see, I already have uploaded to the Blackboard detailed syllabus for the course week by week. So we are already have finished 8 weeks, and we have finished 16 lectures. So today we are starting with the lecture number 17. Okay, the start of the control flow instructions chapter, the second part of chapter number 4. So chapter number 4, as we indicated, is 2 parts, and this is the second part of chapter number 4. The second part of chapter number 4 is actually related to the control flow instructions. And we mean by control flow instructions, the instructions that can change the flow of the program execution. That means this instruction can change the direction of the execution of the code segment, the instructions in the code. So instructions that actually allows the microprocessor to navigate across different instructions within or outside the code segment. Those instructions are actually classified into 2 major sets or categories. We have what's called the unconditional flow control flow instructions, and we have the conditional control flow or flow control instructions. The first and the little bit simpler is the unconditional control flow instructions. We will discuss in this category 2 sets of instructions for jumping and instructions for what is called the call and return from subroutines. We will be switching between the slides and the on-screen board while we are demonstrating the concepts of this chapter. So, as I just mentioned, the instructions that we are about to discuss are changing the flow of the program execution. The instruction that we have learned in the previous chapter was just instructions that perform mathematical or logical operation, as we already learned in the first part of chapter 4. Now we need to get more control on what is being executed. The first set of instructions is what we call the unconditional instructions or unconditional jump instructions. All of the instructions in this chapter are based on a basic operation called jump. So we are in chapter 4, control flow instructions. The most important or the dominant or the basic instruction in this category is the jump instruction. Okay, what is the jump instruction? The jump instruction is an instruction that actually makes the microprocessor to behave different than its regular or conventional sequence of operations. As we already explained before, the microprocessor goes into 3 cycles for each instruction. It's doing fetching, decoding, then execution. And we have demonstrated that in chapter 3 and some parts of chapter 4. Right now, okay, So after the microprocessor finish those three cycles, fetch, decode, execute, automatically, as we have learned and we've seen in the exam, the first midterm, automatically the microprocessor is supposed to go to the next instruction in the code segment. So I have the code segment and I have maybe instruction 1, instruction 2, and so on. Automatically, the microprocessor is doing the three cycles, fetch, decode, execute for instruction number 1. After finishing instruction number 1, what happens? The instruction pointer is updated automatically based on the size of the instruction 1, okay, to point where? To instruction 2. So as we indicated in our last lecture, okay, the execution of the instructions in the code segment is done in which order? In sequential order. Sequential order means after finishing and executing one instruction, it should go to the next, and so on, until the whole program finish. Today, we want to negate this concept. Today, we want to deal with instructions, in particularly jump instruction, that actually allows me to change the flow of the execution of my program. So when I encounter a jump instruction, assume this is instruction 1 is a jump. Assume that instruction 1 is a jump. What will happen if I encounter a jump instruction? That means the microprocessor will not execute the next instruction after the jump. I have here instruction 2. That means what will be executed after the jump will not be instruction number 2. But which instruction? It depends on the destination or the target of the jump. And the jump instruction takes only one operand, and this operand is actually the target of the jump. Target of the jump is supposed to be some location within the code segment. Inside my code segment, this is actually the code segment. Within the code segment, by default, as we will see, is a target location. Okay, so the target location is where the jump should go. So whenever the microprocessor encounters the jump instruction, it's actually expect to see a target. What is a target? It is an address for a location where the microprocessor is ordered to jump to. Okay, so target is supposed to be an address. Address where? Where it's an address in the code segment. Okay, so when the jump instruction encountered, the microprocessor will not do its regular flow of operations. So usually, if I'm assuming that instruction 1 here is 2 bytes, automatically after executing instruction number 1, IP will be incremented by 2. Why? In order to execute, to make the microprocessor point to the next instruction, which is instruction 2, and then the next fetch, decode, execute will be for the next instruction. While when the microprocessor encounter a jump instruction, this means what? This means the new location for the execution is the target. So actually, the IP will not be incremented automatically based on the size of the jump instruction. the IP will take the target address. Okay, so that's it. So jump is doing what? Jump function is basically modify the instruction pointer to populate it with the target location of the jump. Okay, so and this is the most elementary basic jump or control flow instruction. The jump instruction has a lot of applications. Okay, one of those applications is what we call the the call and subroutine pair of instructions. Before we go to this kind of advanced types of jump instruction, let us at least demonstrate a simple jump instruction. Okay, we want to learn the jump instruction. We want to learn what are the different addressing for the jump instruction, what are the different flavors for the jump instruction. Because jump instruction has two main flavors that we want to discuss. We have what's called the near jump, and we have what's called a far jump. So now we are discussing the different types of the jump. We have two types that we want to learn, what's called the near jump and what's called the far jump. Near jump means I am jumping within the code segment. If I am jumping within the code segment, that means the target defined in the definition of the jump instruction is simply an offset. Because if I'm within or inside the code segment, I just want to know how the offset is changing from my next location to whatever the instruction is want to send me to execute. Okay, so this is the first type of the jump instructions called the near jump. The second type of jump instruction is called a far jump. Far jump means I want the microprocessor to get me out of the code segment. Out of the code segment where? As we discussed before, we have 4 segments in my program. We have the code segment, we have the data segment. Definitely, I will not jump outside the code segment to the data segment because data segment contains data. It does not contain instructions. So there is nothing to be executed there. So it does not make any sense to jump to the data segment. Okay, maybe I'm jumping to the stack. No, the stack, we didn't discuss it yet. And we didn't discuss what is the purpose of the stack. So leave the stack alone right now. So what is my fourth segment that we have in our program? It is the extra segment. So I can utilize the extra segment. As we mentioned before, the extra segment is one free segment that I can utilize either for data or for code. If my code cannot fit in the code segment, that means I will start utilizing the extra segment for the code. In that case, I may have at a certain point inside my code to decide to go out of the code segment to go and execute the instructions in the code that I already stored in the extra segment. In that case, I don't want to do a near jump. I do what's called a far jump. Why do we call it far jump? Because I'm getting outside the segment, which is the CS. However, the microprocessor is using the CS by default. IP, this combination is where the microprocessor goes to execute the instructions. So that means I wanted to modify the code segment register, CS register, in order to make it match the ES register if I ever want to do a far jump. Accordingly, far jump is not only providing an offset, it should provide a segment and offset for my jump. And this is the main difference between the near jump and the far jump. Okay, so in the near jump, I expect only to see an offset. For the far jump, I expect to see segment, usually the extra segment, the ES, and an offset. Okay, so um, in order to further demonstrate the jump instruction, study it well. So let's go back to our slides. Let's see what are the different addressing modes that we have for the jumping instructions, the different flavor of the jumping instructions, and discuss the jumping instruction in more details. So right now, I will just share with you the slides in order to uh, go and discuss the slides that are actually describing the jump instruction in more details. So going back to our slides here, we can actually see that on slide number 2, we are just discussing in general the different flavor of the instruction flow control instructions. And we can actually see the next slide, which is number slide number 5. If you just keep hold for 1 second. Okay, so we come back to the slides. We come back to our slides. So we are now on slide number 3. So in slide number 3, we can see actually the two categories of the what we call the unconditional jump instructions. Okay, the first one is the jump, also known in many other architectures as the branch instruction. The jump instruction definition, as you can see here, I have actually the definition of the jump. It is actually using 3 letters, JMP. This is actually the mnemonic of the unconditional jump instruction. And we have different addressing modes for the jump instruction. Forget about the short, we are not studying it. We only stick to the near and the far for either with a label, with memory, and with register. Remember that we want to jump to a new location either within the code segment or outside the code segment. So as we mentioned before, is it easier for me to jump to a location defined by its absolute value of the offset, or it is better to give it a label? Definitely the label will be easier for me as a programmer. So we can actually classify the addressing modes for the jump into three categories. I can uh, jump using label, I can jump using memory, or I can jump using the registers. Okay, so jump, I can either jump to label or jump to uh, of a pointer, some register that actually carries that offset. So either to give the offset as a number or as a label, or give the offset as a dynamic pointer through some register, or even give that through the memory. So accordingly, in slide 6, we can see that jump to a label is done through the change of the instruction pointer based on the target that is given in the instruction. So as the example shows here, JMP, if I use JMP and then I provide some offset here, that means the next value of the IP after executing this instruction will be the offset that is given here. That means automatically the instruction pointer will be updated based on the target of the jump instruction. The second type of jump is what's called the far jump, as we demonstrated on the table. And here I have to provide a new address for the segment I want to jump to. So here the jump instruction not only taking an offset, it should take a segment and an offset. Definitely, or in the common case, this offset is actually, this segment is actually the address of the extra segment, which is stored usually in the ES register. This is what we call a far jump. Okay, I can also make the jump through some register. The register used for the jump here is the BX register. So so that means I have first to populate the BX with the offset that I want to jump to, and if BX, for as an example, contains the value 1, 2, 3, 4, that means the next instruction to be executed after my jump instruction will be the instruction that exists in the CS double dots 1, 2, 3, 4 hexa as the offset. Okay, so the microprocessor now is guided where to go in order to execute the next instruction after the jump. As we just mentioned, I can also use the memory locations in order to perform my jump. So, and here I can perform either a near or far jump. So if I'm using the memory addressing mode for the jump, that means this actually can be performed through a memory address, and the memory address could be either direct or indirect. So in the example shown here, okay, I'm using the indirect addressing mode. That means the address of the offset is given into the BX, and the memory should be accessed. Okay, the data segment is being accessed here to grab in the DS those two memory locations, and the values for those memory locations will be the content of the memory will be used as my offset for the unconditional jump instruction, which is an indirect addressing mode, as we learned before. As we mentioned, jump instruction also can be done as a far. So if I'm using a far jump, that means I'm looking for not only 2 bytes of offset, I'm looking for 4 bytes. 2 bytes for offset and 2 bytes for segment. If I'm doing this through the memory, that means I want to access 4 locations of the memory in order to do my far jump. Okay, the first low order bytes of the memory carries the offset for the target of the jump, and the next 2 bytes are actually carrying the segment. So accordingly, this jump instruction will go to the DS, grab the 4 bytes. The first 2 bytes will be considered the offset. The second 2 bytes will be the segment, and these values will be populating the CS register and the IP register in order to start executing the code from a completely new location far from the code segment. Um, a practical example for the jump is what is shown here in this slide. So here I am populating AX with 5, BX with 2, and I'm jumping here unconditionally to some label called calc_c, as you can see in the third instruction here. So this instruction here, I am providing the offset to the jump, the target of the jump, through a label. So instead of knowing exactly the value for the offset, I just put a label here on this instruction. So when I jump calc_c, that means this calc_c will be translated into an offset, populating the IP, and the next instruction after this jump will be the instruction labeled by the calc. So IP after this jump will be carrying the calc value, and accordingly the next fetch decode execute will be starting from here. The microprocessor effectively jumping to the calc, he will execute this instruction, which is actually adding AX to BX, and then we'll go to execute the next instruction here, which is also a jump. And here we put the label back. Back means the instruction after the jump here. Okay, so I'm jumping back to whatever I have here to find another jump here to stop. Okay, so here I call the jump 3 times. One to jump here to execute this instruction, then jumping back to this, and finally jumping back to the stop. 3 jumps are demonstrated in this example. Okay, I prefer to stop here. So we are actually have covered the jump instructions. So our next lecture, inshallah, will be to discuss the subroutine, the call and return from subroutine, which is kind of a more advanced version of the jump instruction, but it uses the exact same concept. So in this lecture, we just covered the jump instruction and how it modifies the IP to change the location or the flow of execution of my code segment. Okay, so so this is actually part 1 of lecture number 17. We will stop here and we will resume in part 2, inshallah, shortly.